Okay, we're about to do the funnel problem. The funnel. The funnel. How do you spell funnel?
Funnel.
The funnel. Or the textbook will call it the inverted cone tank. Inverted cone tank. I like the funnel better because it'll make you laugh a little bit. This is a big funnel. It's not going to be a little funnel. Okay? Here's the big funnel. We're going to make our funnel 4 feet in radius, so you could actually swim in this funnel, and 12 feet tall. We can do it in inches too, if you wanted to, and we could do cubic inches and make it like a funnel, right? And I'm just going to mention this, and I may be wrong now because I had to think about it a few times, but ladies, don't drink from a funnel when you're in college. Okay? You know, don't drink from a funnel. It just, you know, beer from a funnel, don't drink beer anyway, but don't drink beer from a funnel, you know, especially if somebody's recording. If your dad's going to see it, he's going to smack you. I'm sorry, he's going to be very disappointed in his dear sweet girl. All right? I used to say ladies do not drink from funnels, except I know a lady that's now a Presbyterian minister that is on video drinking from funnels, so I don't know. All right, 12 feet, 4 feet. There's my little rules of college, right? I put that on the video so that y'all can see that y'all need to listen. Now, the problem we have is we're not going to let water leak out. All right? There is a formula for how fast water leaks out based on the size of the hole, and it happened to be water because of the weight. It's called Torricelli's law. And Torricelli's law, I'm not going to remember it now. I'm not even going to remember how to spell it. Torricelli's law gives you the change in volume with respect to time equals, it's the area of the hole times the density or something, some K value, and it's the area of the hole and then the depth of the water. Because y'all realize the depth of the water changes the pressure, right? Fair enough? So when it's real deep, it leaks out a lot faster volume-wise than when it's not. Okay? And that's Torricelli's law. We're not going to use this because we're not going to let water leak out of it yet. But if you did, we'd have to work out the constant for whatever the fluid was, and then the D would tell you the what? Depth. Okay? That's a cool law. Torricelli's law. T-O-R-R. Punch it in your calculator. Look it up before you meet class next time. It'll make me feel good and not feel so bad doing this video for people to look at that are not even in my class that are thinking, how could this guy have been hired to teach this class? Now, we're not going to talk about the change in the size of the tank. We're going to talk about the change in the water in the tank. We're not talking about changing the size of the tank. We're talking about the change in the water in the tank. And here's what we're going to do. We're going to have water pumped into here at 5 cubic feet per minute. 5 cubic feet per minute. And as the water is pumped in there, here's what you're going to notice. When that first 5 cubic feet hits, it's going to get pretty deep in there. Because what? The radius is real what? Small, so that 5 cubic feet is going to take up a lot of depth. What's going to happen when you get up here to where the tank is almost full? It's not going to go up as fast because that layer of 5 cubic feet is going to be spread out over a greater radius, so it's going to have a lower what? Depth. Is that okay? Got the idea? So what we're going to do to make this problem a good problem to compare and talk about and see what happens is we're going to find the change in depth with respect to time equals question mark when, let's do 4 feet and 8 feet deep. Is that all right? 4 feet deep or 5? Let's do 5 and 10. 5 and 10. When 5 feet deep, D equals 5 feet. And then we'll do it again for when what? D equals what? 10 feet. Okay, we'll do an A part and a B part. And we're thinking that the change in depth should be greater here than here, right? Is that okay? That's what we're thinking. So you understand the problem, understand the concept.
You said it's going to be greater when D equals 5 feet?
It's going to be greater when D equals 5, the change in depth is. All right, now, first thing we need to know is the volume of a cone-shaped water. Water's in the shape of the cone, we need to know the volume of the water in terms of what? R and D. What is the volume of, see, I put the 4 and the 12 on there because they're constant, but they're not my water, are they? But what is the volume of a cone? The volume of a cone is 1/3 pi r squared times the height of the cone. But since this is an inverted cone, we're going to put a what right there? A D. That, folks, is the volume of the water in that cone based on this R and this what? D. The funnel. Okay. Now, the problem is, if you look over here, I got D over here, right? I'm talking about change in D. I'm talking about change in volume. I don't have any information over here about the radius, do I? What I would really like to do is figure out some way to rewrite the radius into D. Can the radius be written in terms of D? Geometry.
So 1/3? Yeah, 1/3.
Okay, I think y'all are already there. Okay, R relates to the 4, right? R relates to the 4 as D relates to the what? 12. What am I using when I wrote that? I'm using what kind of triangles? Remember similar triangles? Remember similar triangles, folks?
Yep.
Please realize that ratios like this only work with similar triangles, not other similar shapes. The ratio system like this only works with similar triangles. It doesn't work with similar trapezoids or anything like that. Okay? So you find out that R does equal what? 1/3 of D. That's the key to being able to work these problems, is to get everything into the depth. You got to turn all your variables into terms of D. So the volume equals 1/27 pi D cubed. Don't take the derivative with it written all messed up like that. Turn it into something really simple and easy to take the derivative of. What's Mr. Evans really stressing about these conical tanks? You've got to notice this similar triangle part. You've got to do R is to 4 as D is to what? 12. You've got to see the similar triangles in order to work this problem. That's the geometry you've got to bring with you from your past. Somebody says, Mr. Evans, that's a pretty easy problem then. Change in volume with respect to time is equal to 1/9 pi D squared, change in D with respect to time. And then once you get there, You fill in your information, and you know what the change in D is. The hardest problem, this part of this problem, is going from here to here. That's the hardest part. The calculus is not hard. The hard part is remembering a way to set those up. Now I'm going to let y'all finish working it out for 5 feet. We'll let y'all work it out for 5 feet and see what you get. Change in volume is 5, 1/9 pi, 5 squared, dd over dt, and I get 5 times 9 over 5 squared pi, dd t, 9 over 5. And that's going to be feet per minute, which is not very fast. 9 over 15 feet, 9 over 15, 2/3 of a foot. It's about 8 inches in a minute. I guess that is pretty quick. 8 inches would scare you if you were standing there going, throw me the rope, right? And notice we never used a calculator to reduce that or get that to work out. Now, if you did it for 10 feet, that would be 10 squared right there. So let's see what would happen. For 10 feet, you get 5 equals 1/9 pi, 10 squared, dd over dt. You get 5 times 9 over 10 times 10 pi. Notice I'm making it easy to reduce. Instead of putting 100 there, somebody said, Mr. Evans, you should have been able to do it without that. 9 over 20, 9 over 100, that'd have been 100, right? You gotta put 100 under there. 5 over 20, so 9 over 20 pi. dd over dt. And feet per minute. And notice it is going slower. The numerator stayed the same, but the denominator got larger, so the value got what? Smaller. Right? And it's just a matter, the thing that gets you is you've got to realize all the previous knowledge you have to have to deal with the problem. So far, so good? Someone has a question about where one of those numbers came from. Anyone? So I'm going to add something else to this problem. And you know, you got to do something else with it.
Is that on the right, this one D equals 10?
That's d equals 10 over there. And I'm about to erase the d equals 10 one. We're going to talk about more about just the d equals 5. Okay? We're going to talk about more of just d equals 5. All right. You're looking down in the tank. And you're looking at the layer of water at the very top, which is in the shape of a circle. We're looking at this water circle right here. Is that okay? We're looking at that circle of water as the tank comes up. So would everybody agree the area of that circle is getting larger, that surface? Yeah. What we want to do is we want to talk about the change in the surface area with respect to time when the D is 5 feet. And the reason I'm going to use 5 feet is I figure I'm going to need some information from somewhere over here previously. Well, folks, what is the area of that circle? It's what? Pi r squared, right? Now, if I were working the problem, probably what I would do is I would just go ahead and change r into what? D's, because I got to know my change in D, right? See, if I change that r into D's, then I've got information that I need. Or you can leave it in terms of R, and then you can use your little formulas and find change in R and all that. But I would probably do what first here? Just go ahead and change it into D's. Area equals pi 1/3 D squared. So area equals 1/9 pi D squared. Take the derivative, substitute the numbers in, and you're on your way. But what I want you to realize is you could do it in terms of R, and it will still work. You can do it in terms of R or in terms of D. Is everybody okay with finishing that and knowing what's going on? Okay. I got to show you something here. We're not going to use it on this problem. I got to show you something that'll help you. See this equation? Anytime you have an equation, you can turn it into a rate equation. Make that R equals 1/3 D, and then the change in R with respect to time equals 1/3 of whatever the change in D is with what respect to time. What am I trying to show you there? There's a whole lot of possibilities where if you have an equation, you can turn it into a rate equation and use it when you need it. I didn't need it here because I just went ahead and changed everything into D first. But I would have needed it if I left that in terms of R, because I had to know the change in R with respect to time is what? 1/3 of the change in D with respect to time. And that's what helps you when you start realizing that anytime you have an equation, you have a rate equation. All right? Take the derivative with respect to time. That's the funnel. And I hope that was a pretty good lesson since I recorded it. And I'm not going to record it again for any of these other children, I don't think.